Welcome friends to this second lecture of week 12 of soil science and technology, and in this lecture we will be talking about the different data processing for digital soil mapping, and then we will be talking about different types of continuous modeling for digital soil mapping. So, as I told you that digital soil mapping requires some data processing because all soils are not measured universally at the same depth, because as you can see here there are different horizons like OA, BC, these are the master horizons. However, in the legacy soil data which are compiled by different scientists, you will see some data is available, some data is not available. So, you see sometime the data for O and A is available, however, the B and C data is not available. However, you will sometime you will see O and C data is available, however, B and A data is not available. So, there is a heterogeneity in terms of data availability, and that is why we require some data processing. So, some soils are sampled per all soils are not measured universally at same depth. Some soils are sampled per horizon or at regular depths. Some soil studies examine only the topsoil, while others sample the bedrock depth, and then different soil attributes are measured at some location and depth, but not on others. So, you can see huge amount of heterogeneity as far as the this legacy soil data is concerned. Thus, a number of pre-processing steps are needed to fulfill the requirements of DSM. So, what are these steps? Well, the first step is that soil depth function, and the traditional method of sampling soil involves dividing a soil into profile into horizons, as you can see OA, B and C, and the number of horizon and the position of each are generally based on attributes easily observed in the field, such as morphological properties. We have already discussed that. And from each horizon a bulk sample is taken, and it is assumed to represent the average value for a soil attribute over the depth interval for which is sampled. For example, if we are taking a bulk sample from the B horizon, then we generalize the property of that sample as the representative property of B horizon. However, what is the problem in that case? The first issue is, from the pedological perspective, soil generally varies continuously with depth. However, representing the soil attribute values as an average over the depth interval of horizon leads to discontinuous or step profile representation. For example, we remember that we know that the soil property varies continuously from the top of the profile to bottom of the profile. But according to this bulk soil representation, if we take one sample from here, one sample from here and one sample from here, and based on the measurement of that particular samples, we are generalizing the whole depth, that is the whole horizon. So, that is producing some discontinuous or stepped profile representation. So, that is problematic. So, what if one wants to know the value of an attribute at a specific depth? So, if we want to know the value at this particular depth, what is how it will be possible? It will not be possible if we are taking a bulk samples and generalizing the whole horizon. So, that is why we need some depth function. And let us see what are the other issues. The second issue is difficult for DSM modeling, because observation at each horizon for each profile will rarely be the same between any two profiles. So, observation at each horizon or for each profile will rarely be same between any two profiles. So, these are two issues for which we require some pre-processing, and the solution is, we cannot remember that we cannot ignore the legacy data, because this is the major base data which we require for digital soil mapping. So, we need to derive a continuous function using the available horizon data as input. For example, if in this case we are having the depth data from somewhere between 10 to 30 and then 30 to 60 and then up to 140 or something like that. So, these are our available clay data, and we need to fit a polynomial and exponential decay type of depth function. As you can see, this is a polynomial or exponential type of depth function, this red line, and this is a continuous depth function also. I am sorry, this is a continuous depth function like equal area quadratic spline function. So, you can see here these are the available soil data for different depths, like for say for 10 to 20 and then 20 to 60 and so on and so forth up to 140. So, we are fitting a continuous depth function like equal area quadratic spline function here represented by this red line, and using this continuous depth function we can predict the depth at a particular point. So, this is an example, and let us see in details about the mathematical function. Obviously, this equal area spline, the formula for equal area spline was first we got from this Malone et al. In 2009, where we assume that the measurement of bulk sample from layer I is assumed to reflect mean attribute level apart from measurement error. So, mathematically the measurement can be modeled as yi equal to fi bar plus ei. So, it is assumed that the true soil attributes value vary across very smoothly with the depth. So, the soil attribute varies smoothly from the top of the profile to the bottom of the profile, and this is translated into mathematical terms. So, we denote depth function by x and the depth function describe the two attribute values by fx or function of x obviously. So, which means that f(x) and its first derivative are both continuous and the first derivative of x is a square integrable. So, the depth of the boundaries of n layers are given by for example, xn, xn and xn. So, the fi bar here, this fi bar is the mean value of this fx over the interval of xi minus 1 to xi. So, it is for a one layer, it is the mean value over the interval, and ei is the measurement error. Obviously, this is the measurement error, and with the mean 0 and variance sigma square. So, fx represent a spline function which can be found by minimizing this term, and this term basically represent, the first term basically represents the fit to the data, and the second term measures the roughness function or penalty. So, roughness function or fx. So, expressed by its first derivative. So, the parameter lambda here, basically this is the lambda which is called the tuning parameter. It is basically trade off between fit and the roughness penalty, and the solution is a linear quadratic smoothing spline. So, let us see. So, this is basically the mathematical function of this linear quadratic smoothing spline, and let us see how it will work. So, this is the basically the equal area spline or linear quadratic spline. So, this is a quadratic spline which you use to harmonize the soil data across our desired depth. Remember that this is called equal area spline because for each horizon area to the left fitted spline obviously equal to the area to the right fitted spline. So, that is why it is called equal area. So, you can see this is a spline, this area will be equal to this area, this area will be equal to this area, this area will be equal to this area. So, that is why it is called the equal area spline. The another name of this spline is called mass preserving spline because the original data is preserved and can be retrieved again via integration of the continuous spline. So, the spline parameter are the value of soil attribute at the standard depth that are specified by the users. Okay. And remember that using the spline profile, using this mass preserving equal area spline, you can harmonize soil profile data and model at a specified depth. So, as I have told you, the global soilmap.net project is a global consortium that aim to make new digital soil map of the world using the state of the art and averaging and in these emerging technologies for soil mapping and predicting soil properties in fine resolution. They have prescribed some 6 standardized depths. These 6 standardized depths are these 0 to 5 centimeter, 5 to 15 centimeter, 15 to 30 centimeter, 30 to 60 centimeter, 60 to 100 centimeter and 100 to 200 centimeter. So, if our profile data looks like this, the original legacy data looks like this, it is possible by using this equal area spline to get the continuous value or of this particular parameter up to our desired depth by fitting this equal area spline. So, guys, another important aspect of data processing is intersecting soil point observation with environmental covariates. So, in order to carry out DSM in terms of evaluating the significance of environmental variables, in explaining the spatial variation target soil, the target soil variable under investigation, we need to link both sets of data together and extract the values of the covariates at the location of the point data. Obviously, as you can see, as we have discussed already, the workflow of DSM, the first starting point is our legacy soil data, and remember all this legacy soil point data is is associated with some x and y coordinate data, because we are using our GPS receiver to measure their coordinates. So, once we measure their coordinates, the next step we can see we are stacking all the covariates data, and it is required that the covariate values from the grids, once we stacked all these covariates, the next step we have to extract all the covariates values which is available for this particular soil point data, and all these will be related by these x and y coordinates. So, again, once we get the legacy soil data and their coordinates, the next step will be to extract the soil covariate information for those particular points. We do not need the soil covariate information for all the area, we only need the soil covariate information for those particular points for which the legacy soil data is available. So, we call it intersecting, and this is another major pre-processing step before we go for digital soil mapping. So, in a nutshell, obviously we will start with this XY data, we will start with this geo data, legacy soil data, and then we will fit a mass depth integrating function or equal area spline to get the depth wise values of that variable up to our desired depths. There are 6 desired depths as proposed by globalsoilmap.net project, and once we harmonize all the profile data up to that standard depths, the next step is to stack the covariates and extract the covariate information for those particular points for which we have the soil point data. Now, once we get this thing, then we will use this in the spatial prediction model using some mathematical function to produce the 3D maps of soil for that particular property. So, this is in a nutshell about the workflow in the digital soil mapping, and so we have covered the basic overview of digital soil mapping. The next and very important topic in digital soil mapping is modeling and mapping of continuous variables, and in this we will be discussing about the model validation, and then what is multiple linear regression, what is decision trees, and what is CART, and also we will be discussing about random forest in brief also. So, guys, if we talk about the model validation, let us see what is regression. Now, in the regression, basically we are interested to predict certain variable using another random variable. So, for example, if we have two variables, say x and y, or in other words, say y is our as far as the soil data is concerned, for example, soil organic carbon, and x is our, for example, let us say it is soil clay. So, if we want to have, for example, we have 100 soil samples, and for 100 soil samples we have 100 records of organic carbon and 100 records of corresponding clay content. So, if we want to predict this y or target variable using our independent variable, let us see this y is our target variable and x is the independent variable. If we want to predict or if we want to make a relationship uh, where we will predict the y in terms of x, that is called regression. So, simple linear regression basically takes the form mx plus c, or here y is our target, x is the predictor, m is the slope and c is the offset. Now, you can see here this is the regression in a nutshell. Obviously, in the x axis these are the predictors, in the y axis this is the target variable, and ultimately we try to fit a linear regression, we try to fit a linear we try to fit a linear relationship. As you can see here, this is the straight line and it has a the representation of bxi plus alpha. Obviously, alpha is the offset and beta is the here the slope. So, this is called regression. This is the simplest form of regression, and in case of multiple linear regression, when there are more than one predictor variable, then we call it multiple linear regression. So, guys, this is the overview of regression, and why we are discussing this. Let us see. Now, if we go back, so once we create a model for predicting a particular soil property, why we create a model? We create a model so that it can generalize or it can predict any particular property using some unknown samples. So, that is the major use of creating a model. So, once we create a particular linear model or any other nonlinear model using some soil data or soil covariate data, the next step is to ascertain their accuracy, model accuracy. Now, the model accuracy can be calculated by model validation statistics. The model validation is basically the appraisal of the usefulness of the model, or in other words, whether the created model or calibration model we call it, the calibration model can be used to generalize or to predict any unknown sample that can be that can be predicted via validation. So, there are several important points obviously. Like root mean square error, and root mean square error can be obviously you can see this is a formula of root mean square error, and this is one of the major important index of soil index of model validation. We always want the root mean square error to be minimized, because the less the root mean square error, the more accurate the model, and also bias, which is called the mean error of prediction, and it is defined by this formula. And then Pearson correlation coefficient. Pearson correlation coefficient basically shows the strength of linear relationship between two variables. So, this is another index of model validation. And then Lynch concordance correlation coefficient, which is a single statistic that both evaluates the accuracy and precision of the relationship. Remember that it is often referred to as the goodness of the fit along the 45-degree line, thus it is probably a more useful statistics than the R square alone. So, if we consider this x and y and we create a model like y equal to alpha plus beta x. So, this will be a linear regression, and in this linear regression obviously remember that these are some important indices like R square, RMSE. Remember that R square measures the strength of the regression relationship, and R square varies from 0 to 1. As R square tends towards 1, the model is more accurate, and as it goes towards 0, the model is there is no relationship. and RMSE is also root mean square error. As you can see, this is root mean squared error. So, obviously, this is an RMSE, and RMSE measures that what is the strength of this linear relationship. So, these are some important indices of model validation, and they have some specific values which generally tells us whether that model is good or bad. So, let us see what are the different types of model validation. Model validation is of two types. One is basically the first way of doing the model validation is using some additional independent data set, which is basically unbiased, and we can draw that by simple random sampling and or stratified random sampling. This is the best way. I mean, you create one model and then you draw a random sample or independent data set, and which is unbiased, and you use this independent data set to judge the accuracy of your created calibration model. So, this is the first way, and this is the most important way. The another is the data subsetting, and we will be talking about it in details. So, the data subsetting basically are of three types. One is random holdback or holdout, and then k-fold validation and leave one out cross validation or LOOCV. Now, in the random holdback or holdout, basically we divide the data into 70% and we create the model using this 70% data. We call it calibration data set. The rest 30% of the data is used for validating the model. Okay. So, let us see them one by one. So, model validation basically asks whether can we fit our data into this model. So, for example, here there is a particular example, it is an independent variable and this is a dependent variable. The question is, can we learn or create a relationship that fits our data y equal to fx plus noise or fx plus error. So, you can see there are three different relationships. One is linear relationship, another is quadratic relationship, another here you can see piecewise relationship. So, let us see them one by one, and our question is which one is the best. So, you can see what do we really want. So, why not choose the method with the best fit of the data. So, our intention is to select the best model which can generalize this behavior either linear or quadratic or piecewise linear. So, first let us see what is the holdout method. So, the holdout method is the simplest kind of cross validation. The data set is separated into two sets randomly sometimes called the training set and testing set. Training set another name is calibration set, and testing set the other name of testing set is validation set, and the function approximator fits the function using the training set only, and then the function approximator is asked to predict the output values for the data in the testing set. So, let us see this in the step by step. So, let us see this is tested method. So, randomly in the first we randomly choose 30% of the data to be in the data test set and the remainder is in the training set. So, as you can see these blue dots are basically the training set and these red dots are the test set. And in the next step is learning the model from the training set. So, once we created this division between the learning or training set and the test set, let us use this training set to create a first model y equal to alpha plus beta x. So, this is our next step. The next step says estimate your future performance with the test set. So, once we create a model, now let us use our test set to use in this particular relationship to predict, and then let us estimate our future performance with the test set. For example, if we have created a particular model, for example, y equal to say for 3x plus 2. So, here we will then input. So, this is our calibration model. Now, once we create this calibration model, let us input our validation data points or test set into this relationship and get some values. These will be predicted values. So, once we get the predicted values, we also know their original values. So, let us make a relationship, let us see how they are accurate or not, or let us make a relationship between the predicted and actual. So, this relationship is called the validation relationship. So, again once we create the training model or calibration model, then we will estimate our future performance with the test set, and then we will calculate the mean square error by using this particular formula, and then mean square error obviously, and then we will estimate our future performance. So, in this case our mean square, a particular example mean square error is 2.4. So, this is an example of the random holdout method. Second is test set method. So, randomly choose again, and this for quadratic function, this similarly just like we did for linear regression, for this for quadratic regression, this is for piecewise regression, and ultimately we will get an estimate of mean square error. You can see in the first linear regression we are getting a mean square error of 2.4, and in the quadratic method we are getting a mean square error of 0.9, and in the test set, in the piecewise method we are getting a mean square error of 2.2. So, according to by seeing this result, we can say that this quadratic function shows the best fit of in the available data. Now, obviously there are some positive things and negative things in this test set method. The positive things are they are very simple, and they can simply choose the method with the best test score, and the problem is there is wastage of data. That means, best model is estimated using only 30% less data, because we are using only 70% of the data, and if we do not have much data, our test set might be just lucky or unlucky, because it may be possible that the test set samples are completely different than that of our calibration set, and as a result of that there will be complete mismatch, and the model validation will produce very poor results. The second method is called the holdout method. So, advantage of this method is that it is usually I am sorry, it is the previous method, holdout method, we have not gone to our next method. So, the advantage of this method is that it is usually preferable to the residual method and takes no longer to compute. However, its evaluation can have a high variance, and the evaluation may depend heavily on which data points end up in the training data set and which end up in the test set, and the evaluation may be significantly different depending on how division is made. So, it is very important. The second method is called the k-fold cross validation. Now, k-fold cross validation is one way to improve over the holdout method, and the data set here is divided into k subsets, and the holdout method is repeated k times, and each time one of the k subset is used as a test set, and the other k minus 1 subset are put together to form a training set. Then the average error across all the k trials is computed. The advantage of this method is that it matters less how the data gets divided, and every data gets to be in the test set exactly 1 and gets to be in a training set k minus 1 time. So, as you can see here, this is an example of this k-fold cross validation, and in the k-fold cross validation let us divide. For example, this is our total data set. Let us randomly break the data set into k partition. In our case, let us do 3 partition, and we denote them into red, green and blue. And in the second step, for the red partition, let us use the for the red partition, let us train all the points not in the red partition, find the test set sum square error on the red points. So, basically what we will do, we will use all the green points and the blue points as our training points. We will fit a training model, and then we will produce, and then we will see the error from the by using these red test cases. And In the next iteration, we will do the same using the green samples, and the last step we will do the same using the blue samples. So, you can see in each of the step we are holding one particular set. In the first time we are holding the red set, in the second time we are holding the green set, and the third time we are holding the blue set as test set, and we are using the rest of the two for creating a calibration model, and then we are producing the we are estimating the error. So, once we complete all these three iteration, we will have an average, and then this will be our mean, and this will give us the mean validation performance. So, this is about the k-fold cross validation, and the k-fold cross validation says the variance of the resulting estimate is reduced as k is increased, and the disadvantage of this method is that trading algorithm has to be rerun from scratch to k times, which means it takes k times as much as computation to make an evaluation. A variant of this method is to randomly divide the data into a test set and a training set k different times, and the advantage of doing this is that you can independently choose over large large each test set, and it is how many trials you average over. The finally one is leave one out cross validation. The leave one out cross validation is another form of k-fold cross validation, where k equal to n, and basically here what we do, from the whole data set we select only one sample as a test sample in each iteration, and then for example, there are if there is an n sample, we will select at each iteration we will select one sample as a test sample, and then we will use the rest n minus 1 sample as training sample, and we will use this n minus 1 sample to create a calibration model, and then we will estimate the error using this one sample which we used for testing, and then we will repeat this for all the samples, and ultimately we will predict the mean error from by averaging all the errors from this each iteration. So, you can see this leave one out cross validation, we are leaving one out each time, and then we are creating a model, and then we are estimating the error, and this is an extension of k-fold cross validation. So, that is why it is called leave one out cross validation. Sometimes we call it full cross validation also. So, this is a overview of leave one out cross validation, you can see, and the selection criteria, in which case you will use which one. So, when there are a very few data to work with, obviously you will go with the leave one out cross validation. When we can sacrifice a few data points, obviously we will go with the random holdout or k-fold. However, in case of random subsetting, there is a chance of biasness, because we do not know in case of random subset which one sample will go to the test set and which sample will go to the training set. There could be complete mismatch. So, this is the advantages and disadvantages of this method, and you can see here this is a MLR, multiple linear regression, and this is a MLR example of in digital soil mapping. Here we regress a target variable against more than one covariate, and we use all the covariates, and there are two ways we can do this multiple linear regression. We can use either all the covariates as the predictor, or we can use stepwise linear regression. As you can see, this is a multiple linear regression predicted soil organic carbon stock in 0 to 5 centimeter. So, this map is produced by multiple linear regression, and also this multiple linear regression can produce, not only it will give the prediction for the 0 to 5 centimeter, you can see it also produces the lower limit of prediction, and not only it gives the multiple the prediction for the soil organic carbon stock for 0 to 5 centimeter, it also gives you the prediction interval, that is lower limit of prediction as well as upper limit of prediction. So, you get a sense of the uncertainty in this DSM product. So, guys, let us stop here and we will start from here in our next lecture, and we will try to finish this continuous model and categorical model in our next lecture. And I hope that you have learned something new, and in the next lecture we will talk about different types of nonlinear models also. Thank you very much.